we have a different device, we could actually measure that. So perhaps in the future. Oop. And that water's really close to the top there. Cooper?
So if we were if we were doing the third harmonic experiment, and we brought it back up to 16.6 centimeters, would it be allowed there too? Like, is there several points?
Yeah, so whatever the first harmonic is, there should also be allowed point 3 times that, and then at 5 times that, then 7 times that.
And if there was hypothetically infinite tube and infinite water, it'd just go on forever?
Yes.
Okay.
And since we're dealing with hypothetical, let's assume that none of the sides don't absorb any of the vibrations, and so we can still hear it.
Is this what the lab was gonna be?
Excuse me?
Is this what the lab was?
Yeah, there is a lab where you do this. There is an issue with at least one incarnation of the lab, the fact that there's a couple of false harmonics, which I haven't fully formed about why they happened. I think it might have something to do with some vibrations going horizontally here instead of the vertical ones. But if you misidentify, say, where the first harmonic is because you hear this false harmonic, then that means all the rest of your measurements are off. So it's one of the few, if not the only lab, where it's nice to know what the ideal answer is, just to know whether your measurement is legitimate or not. Other questions? There is one more problem. So the question I'm going to sort of pose to you right as I go to my office: what happens when sound waves meet? And we sort of answered that already, but think about that.
Oh, well, that's it. It's either constructive or destructive. It's either constructive or destructive. But it could be like,
I don't see how
they cancel out.
I don't see how two compressions can come together and cancel out. Yeah, but that's because the headphones said.
Actually, we have answered it before. What happens when sound waves meet?
They interfere.
Okay. So I have 2 waves here. Apparently, some of it got a little wet. 2 waves here that are not the same. They're close to each other, but not quite. And if you can't tell the difference between them right now, might be helpful there. They both start off at the midpoint here, but they end differently. This ends right at the bottom, and this ends on the way down. So they're slightly off. Now, I then took this one and I traced it onto a transparency, or on a transparent folder. Get that lined up. And hopefully you can see that there's a difference here, that I have them starting close to the same spot, they peak in the same spot, but the peaks get farther and farther off as you go. And I don't know, I guess, can you see it in the back there?
Barely.
There. Looking at the fact that the peaks start out much more in sync, but slowly the peaks get out of sync.
Yep.
Can you see it over there? All right. So if I add them together, because you can add them together by, as sort of talked about in the principle of superposition, if you add them together, you get this. Notice that the peak here, the peak before was at 1, The peak of the sum of the waves is near 2, and it's slowly getting smaller and smaller. If I extended this, it would look like that. Where what I showed you before was up to somewhere around here, but if you just kept going. So this is sound, so if they're playing at the same time, it's twice as loud as was before, but what's happening here?
They're canceling each other out.
And so what would you hear? So let's hear what that sounds like. Assuming you've never experienced silence before. All right, so here's 440 hertz. All right, so let's see if we can get sound. That's 440 hertz. Here is 439.5 hertz. I assume you can tell there's clearly a difference between those two. Well, I do have some students who have really fine sense of hearing and can actually tell a difference there. I cannot. Anyone in here actually able to tell the difference between those two?
Play one and don't tell us which one it is.
Say it again?
Play one and don't tell us which one it
Yeah,
is.
play them back to back and then we'll tell you which one.
Was 440 second?
Yep.
Yeah.
All right. However, there is a way to tell that there is a difference there. Let me play them at the same time. That's the 439.5, and here's 440. So you get that constructive interference down to complete destructive. All right, so the combination also has its own frequency. So let's get into the sophisticated math of that. So one was a 440 hertz. The other was 439.5 hertz. Here's the sophisticated math. Let me know if you don't get it. I subtract them and I get 0.5 hertz. Now, was the frequency of what's called the beat frequency, was that a half hertz? Well, another way of looking at that is if that's the frequency, the beat frequency, the beat period, is 1 over the beat frequency. So 1 over 0.5 or 2. In other words, it should get quiet every 2 seconds. Or loud every 2 seconds. Let's see if that's what we got. 439.5, 440, 1001, 1002, 1001, 1002. So, it seems to work.
Dr. Fox?
Yes.
Whenever we're doing that, if we were to do it as accurately as possible, would we have to take the temperature of the room?
The frequency should not depend, because I've created the frequency from here. No, we would not. Speed of sound is not entering into these calculations. I tried to think if temperature would affect it somehow. Not within my experience. If I asked what's the wavelength of the two sounds, then we would have to know the speed. All right, so way too short. Here we go. All right, so now I'm going to play this, and it's going to start at 0 hertz, which presumably you will not hear. And then it's going to constantly get higher and higher frequency. So you'll be hearing a higher and higher pitch. At some point, you will not be able to hear it. So what I'd ask for you is when it gets to the point where you can't hear it anymore, just raise your hand.
Are you doing this on YouTube?
No, it's not a YouTube.
Okay.
It's something called online tone generator.
Okay.
3,000 hertz, 4,000, 5,000, 6, 7. All right, I'm out. I'm going to come back in a couple thousand. It's 10,000 hertz. 12. 13. Just under 15.
Oh. Wow, hurts.
16. 17-ish. I don't suppose, Cooper, you're the oldest student.
I don't think so. I'm 18.
Anyone older than 18?
I'm 19.
It's usually not a good test here. If we had a wide variety of ages, it would typically, the older you are, the sooner you sort of drop out. Because the, whatever they're called, we have people with life science background here, what is it just on the other side of the eardrum that picks up the signal, transmits it to our brain?
Or
If you said it with confidence, I'd believe you. Probably repeat it.
Like one of the 3 bones?
Pardon?
Like one of the 3 bones?
There's some nerves right on the other side of the ear that get damaged over time. I mean, just-
Aren't they like little hairs? I'm not sure what
that's
that's called.
Okay. Apparently, I've been told before, but I never remember.
yeah, it's the conglia. I think it's like pronounced.
That's the mode?
Yeah, it's like a bunch of nerves that receive the sound.
Okay. And so the older you get, you start losing some of the higher pitches. When I was growing up, I could hear when my dad was watching TV downstairs, no matter how low the volume was, I could hear the high-pitched whine that he could never hear. But being an English major, he never quite understood how I could hear it. He couldn't.
So how does hertz work in like visuals? It's like there's like a screen is considered hertz.
So you've got a couple different things there. So as what we're sensing in terms of vision are electromagnetic waves, they're not mechanical waves. So they'll come in and our bodies have evolved to where we can, what we call see, within a very narrow band there. Because it deals a lot with the absorption of the eye fluid. And then there is the refresh rate on computer screens or things like that, if you look at, actually any of the videos that I've done, it's basically taking a snapshot every 60th of a second. And so it's just a bunch of still frames that run fast enough, or run in sequence, which make it look like it's fluid motion, but it's just a bunch of still frames. So there's the refresh rate of what our brains can process. think there's my answer. I don't know if you wanted more or.
No, I understood, that's what I was.
Okay. Okay, other questions up to here? All right, so based on what we've done, suppose I had something with two free ends. What would be the simplest, the first harmonic? What is the simplest pattern? Two free ends. I heard someone say something, I don't know if they're, okay, I'm still thinking it out.
Would it be like two parallel lines?
No, I see where you're coming from on that one, but we are dealing with a wave, we're not just.
Would it be like a helix shape? Like that?
That would,
Like an X maybe?
yeah, something like that. You have the two antinodes on the outside. That's an important thing there. It's more like that.
That's kind of what I was going for.
Yeah, I mean, you sort of do I guess
No,
sideways.
I meant the first one.
All right, so it's generally drawn like that. We have antinode, antinodes, and then a node ending here. How many waves is this?
A half.
Yeah. So if that distance there is L, L is equal to a half of a wavelength. So the wavelength would just be 2 times that length. Let's make a prediction. I just happen to have a device with 2 open ends. You can hear some of the harmonics. That's actually the second harmonic, third, fourth, fifth. All right. And it's probably incredibly annoying for them. So let's, first off, what's happening here? Why does it work at all? As I spin this, as I spin it around, this end is going far faster than this end is. Because it's spinning faster through the air, it actually has a lower pressure at this end than this end. And so with higher pressure here and lower pressure here, air gets sucked up through the tube. Now for the first harmonic, we'll make our prediction, but the first harmonic, I have to spin it so slowly, not enough air can go through really to get the whistling sound. It's like if you have a whistle and you try to blow in it very softly, you won't really hear anything. So, making our prediction. What was it was 344.15?
344.38.
38. So that's the speed. The length, no, that's the length right there. And, okay. So I'm not seeing the meter stick. Length 84 centimeters. .84 meters. And I would expect the wavelength to be twice that for the first harmonic. So the wavelength, I'll put a little 1 there for the first harmonic. This should be twice 2L, which is 1.68 meters. If I know the wavelength and I know the velocity or the speed, I can predict the frequency that we would hear. Because I know that speed is equal to frequency times wavelength, or the frequency would be the speed divided by the wavelength. So 344.38 meters per second divided by 1.68 meters. And what do you get? Louder, please.
205 hertz,
Let's go 1 decimal place.
0.9,
205.9,
well, it's 0.99.
205.99. Okay, so 206 rounding off.
Or 204.99.
Okay.
Yeah.
So this is what 204.99 sounds like. It just doesn't like the tone pad. That would be the first harmonic. See if it sounds the same. We nailed that. All right. I think it's clear that that's not the same. All right, so let's predict the second harmonic. How many wavelengths will the second harmonic be?
2.
How'd you get 2?
Well, because the first harmonic is 1 wavelength.
The first harmonic is a half wavelength.
1.
Yeah, you add a half wave, you're gonna add a half wave every time. The way it would look would be, so this would be the second harmonic. Or L is equal to twice that, or 1 wavelength. And doing the fancy math here, a wavelength is equal to 1L. So I would expect the wavelength to be 0.84 meters. And so the frequency I would hear for the second harmonic would be 344.38 meters per second, divided by my wavelength, which is 0.84 meters.